Okay, so the problem that we were trying to solve previously was very simple. It was this Laplace kind of problem, right, over Dirichlet boundary conditions. Right, so these were our two Dirichlet boundary conditions, and this was our Laplace problem. So now we just want to make this into a Poisson kind of problem. So we just want to change this into some source term, right? So this f could be, so we'll just begin with some kind of a linear function, which is also a constant function, right? And then we'll again keep the function linear, but we could just change it with x and y coordinates. Okay, so we'll look at this test case first, and then this one. So we really want to break this down, break this problem first into two parts. So let's just do that. So let's write this down into our finite element formulation. So this is our stiffness matrix. This guy is our force vector, right? This is our unknowns vector. So now let's just break this into two parts. So here W is basically this problem, which is exactly this, the same kind of problem, but just without the source term. We are again solving it once again on the same Dirichlet conditions, right? So this is the problem without the source term. We solve this, and then we go to this guy. Okay, so let me just rearrange this. It's equal to f minus k w, right? So let's just call this as b, right? So this is the simplified problem which I want to solve. Okay, so more precisely, I am just interested in expanding UR as a linear combination of phi, right? And phi are your eigenvectors. Okay, so these are your global vectors which are spanning your entire geometry, and I want to compute these coefficients and then just expand UR as a linear combination. Okay, so this is my problem statement, and now let's see quickly how to deal with this. So first step would be, of course, to solve your del square W is equal to 0 at our boundary conditions, right? So first we just solve this. Next part we do our same SLEP-C solver, right? So we can compute our eigenvectors, eigenvalues, right? So we get these guys. So next step would be to just go back to the equation which we started off. So I think I made a mistake. I think first we should just normalize this. So first we just normalize phi so that we get this kind of, right? So so basically after we normalize phi, that is, we just divide by a constant, so we get this kind of a nice property, because phi are basically our so they are our eigenvectors which are coming from our FEM solution. So you have this mass matrix as well, and you don't straightforwardly, you don't have this property coming out, right? So you have to normalize them first, and then only this will work, right? So this is simply like multiplying both sides, rather dividing both sides by a square root of your, you could take the L2 norm, or you could also take the M norm, right? So really the idea is to take the inner product of these guys and just ensure, and just take the square root and then just divide by divide phi by this one. Okay, so this will just do the normalization, and we'll see how this is done in the code. So this will be more clear. So we do this normalization, and this will ensure that we get this Kronecker delta kind of property. Otherwise you will just have constants there. Okay, so we should also note that this mass matrix we can also lump and make it into a matrix which just has diagonal elements, and then we could also just take a constant value out, and that would be a lumped approach. But here we are looking at a full mass matrix approach, so that is why we are just writing down this mass matrix. All right, so that is your third step, and the fourth step would be again writing out this guy, right? And I want to expand UR as a linear combination, right? And since K is a linear operator, I can just manipulate this by taking this inside and then going back to this second equation. I can just change this to right. So this is now much more simplified, and we have our Kronecker delta property. So we just so the next step is just to project. So we project this onto our test functions, and our test functions are very similar to our Galerkin case. Our test functions are just going to be our trial functions. So these are our trial functions, and our test functions will be just the same. So we just project onto these, and then we use the Kronecker delta property, right? So we have already seen this guy, right? So this is our Kronecker delta property, and once I just project onto these phi, right? So, and this is the summation, right? So only when the indices match you will get 1, and when the indices don't match you get 0. So this will just reduce to a very simple kind of equation, which is just ck lambda is equal to phi t into b, right? So from this I can just get my ck value, and then I can just express u as w, which you call as a lifting field, plus summation of these guys, right? Our linear combination of phi using these coefficients. So of course I can choose the number of phi that I want, and that is why it's a reduced order model, because I'm not using all the possible combinations of phi, but I am just using few combinations. So I might be dealing with a problem which has like 5000 DOFs, but I will just use maybe 5 global vectors, right? So eigenvectors are global, so I'll just use 5 global vectors. So this is a reduced order system. So now that we know what's happening, so let's just go to the actual code, and let's see what's happening. So I'll just need to share my screen once again. Yes, so right, so this is our, so this was the previous problem. So now in this problem, now you can see that we have just modified the previous one. So the modifications are really, first you are just adding this lifting field. So we had this Laplace problem which we solved exactly like this, but now we are calling it as the lifting field W, which we just discussed, and we have a source term which is constant -1. So we'll change this to an expression just in the next code, but let's keep this simple here, just a constant -1. And since we are going to use the SLEP C, again we have just initialized again this stiffness matrix as a pit C matrix. We also build the mass matrix once again, really the same kind of problem, just that here we have solved the full FEM solution. So this guy which we were solving previously, this was our Laplace problem, and we have just added a source term and solved this problem once again. So this is our full FEM solution with the source term, and we'll compare our reduced order model with this solution, right? And so again the same snippet for your eigenvalue solution, same as before using the SLEP C. And now we have got this solution, but we want to really extract. So this is the guy where we extract lambda and phi, which we want. So these are the eigenpairs, and here we have we are running a for loop because we have just chosen the number of eigenpairs that we want to extract. So we can just run this for, let's say, 5 eigenpairs, right? And so we'll just extract these lambda and phi values for five of these eigenpairs, right? And so now here you can see this is the normalization. So we have just taken the inner product here. So phi, so this syntax is just the inner product, or the dot product, you could say. So phi is dotted with m into phi, right? And so this will give you a matrix which is not an identity matrix. So we'll just take the norm of this and just basically just divide it, right? So if you don't take the square root, this will just be a norm which is of the square value, right? So we have to take the square root, and this syntax just says that give me the phi value divided by this guy. Okay, so this is just like phi is equal to phi divided by this guy, right? So so this is our normalization. So now our phi are normalized, and we can get our Kronecker delta kind of property. And so now we can again take the inner product, which means we are projecting onto phi, right? Because the trial and test functions are the same. Okay, phi are both the trial and test functions. And then finally we are representing UR as a linear combination of our phi with the coefficients. So this is the process of our reduced order model. And now let's just run this code and let's see what's happening. So I'm sorry. So this is our solution, FEM solution with the source term, right? So that is why you're seeing some minus values, because we have put a -1 source term. And this is our 5-mode ROM. You can see that almost it is the same, because this is a very simple diffusion case, and you can see that it is modeling really well. But here you will see the actual error, and this is the L2 error. So you still have a fairly large amount of L2 error if you look at it from an error point of view. And you could just crank up the number of modes. And this will give us our 30-mode ROM, and you can see that this has a much better accuracy. So really this is just a very simple problem with pedagogical value. So it won't be so simple in the industry. So you will have much more complicated non-linear kind of scenarios. We are here just dealing with linears. That is why you can see that all of these eigenvalues are really very well behaved. All of them are positive, right? All of the lambda values are positive. So let's also just add in some variation in the source term. So this code is just the same as before. I have just added an expression here. So the source term is now just having an expression here, x cube into y. Okay, so let's just run this as well. So this will be slightly more difficult to model, because now you are asking your ROM to capture the variation. I think this is... So you can see these are the total number of DOFs. So there are 5,000 DOFs, and we are trying to represent it with using just 30 global vectors. So now you can see that the error is slightly higher. And if I were to use just a 5-mode ROM, so then of course the error will jump up, right? So you can see that the ROM is, so this is -400, -375, so this is 400, 500. So you can see that the scale bars are off. Though the solution distribution is more or less the same, because you have used still 5 global vectors. So you can see the gradation is correct, but you can see that the values are off, and you are seeing, of course, a much higher error, right? So this is a very simple way of motivating the concept of ROM, and of course in industry this is going to be much more complicated. You are going to have not just 5,000 DOFs, right? You are going to have millions of DOFs and complex non-linear problems. And you are going to basically take snapshots and develop a set of a set of basis vectors using POD kind of techniques or much more advanced techniques, and you would again project it just like basis functions, build a reduced order model, and there you would see a much a bigger benefit of this. So you would go from millions of DOFs just to maybe a few hundred, or maybe 100 or even less number of eigenvectors, right? Modes. So this is really a growing field and a very interesting field. Right now it's contributing a lot. You can see there are fantastic softwares like ANSYS Twin Builder, right? So you can use this to set up alarm kind of systems, or even model how your clean room or how your cold room, what are the temperature gradients, and if it is really not cooling well, or you can see hot spots or cold spots, you can just give off alarms before something happens. So really useful from a technological standpoint, and this is just a motivation towards what we are doing. So we are just creating a set of global vectors which are orthogonal to each other, and we can represent them as trial and test functions, and just projecting onto those functions will give us a reduced order model, right? So that's really the idea, and this is where I end this bunch of videos, and in the next bunch of videos we'll look at the Navier-Stokes equations. So we'll code them from scratch, and towards the end, of course, we'll start using FEniCS once again, and at that time let's see if we can take some snapshots and also export that to MATLAB, where we have a POD function. I think it's recently added in the last year. So let's try to use it and build again a reduced order model with slightly more complexity, so that will be more fun. So I hope these videos were helpful, and I take my leave. Thank you for your attention, and I'll see you again.